selection for a modern wind turbine blade. Obviously, there's a lot of different factors that go into selecting that material, and we're going to be talking a little bit about that today. Hang on, it's not wanting to advance slide again. Hang on, oh, there we go. Okay, I'm restarting, apologies.
We're good.
Okay. Hello, this is Group 5. Today we're going to be talking about material selection for a modern wind turbine blade. Obviously, a lot of different factors go into that, and we're going to be breaking that down into multiple design constraints. But first, a little bit of background. We want to determine a reasonable material manufacturing method and an approximate cost for one horizontal axis wind turbine blade. Some immediate thoughts that come to mind are that the blades must be stiff against the wind, and we generally want to avoid plastic deformation, along with a variety of other different material constraints that allow us to narrow down and focus and hone in on one particular material to make these blades out of. But first, the kind of model that we're using, we're assuming that we have basically a beam in the worst possible position, perfectly vertical, with a uniform distributed pressure from the wind acting on the blade. We define the blade length as being equal to 50 meters and a width of 1 meter. We, of course, also define a maximum thickness of the blade being B. From this free body diagram, we can also note the restoring moment from the blade base to resist the uniform pressure distribution. So our first design criteria to help hone in on some particular materials is the fracture toughness limit. Obviously, we need to think about is that pre-existing flaws can cause the blade to fail by rapid fracture. Thus, we set a fracture toughness minimum of 15 MPa meters to the 1/2. And then using CES Granta, the level 2 database, we can quickly find that only 31 materials pass this constraint. Also, eliminating the ceramics, foams, elastomers, and polymer families, leaving only the metals and the composite families, which is all we really focus on for the remainder of this analysis. For the deflection limit, we perform our first translation. We want to produce a wind turbine blade that produces maximum power, and we're constrained by the geometric constraints that the deflection of the blade must be less than 1 meter, and we define the wind velocity and the pressure generated by the wind is 375 pascals at 50 miles per hour. We want to minimize the mass in order to have a low rotational inertia so that the wind turbines can accelerate quickly, and we leave the material and thickness of the blade free. Doing this, we can quickly see and perform our translation from beam theory, and then inputting our boundary conditions, we can derive a deflection limit at the very end of the beam at the point furthest away from the blade base, rearranging this equation in terms of B, and then plugging into our objective function, we can separate the material index for maximization as being the Young's modulus to the 1/3 over rho. Finally, we can also derive a stiffness expression in terms of the force divided by the deflection. And finally, from our deflection expression, we can determine a minimum Young's modulus based on the maximum thickness, B being 0.5 meters, of approximately 2.8 times 8 pascals. So doing this, and for each of the materials remaining in the metal and composite families, we can kind of see what the best performers are, being CFRP, wrought magnesium alloys, and the rest here on this table. We perform the material index calculation for both the perfect minimum and the perfect maximum being, for example, the absolute maximum Young's modulus divided by the minimum density. Then furthermore, we take the mass maximum and mass minimum, which are conversely related to the opposite material indexes. For example, the mass maximum is calculated using the minimum material index, or the worst performer, and conversely for the mass minimum is calculated with the material index max or the best performance. Plotting this with a slope line 3 coming from the 1/3 power on the Young's modulus, we can quickly evaluate that the materials furthest away from the line as we move up and to the left are our best performers. Note that GFRP would in theory, be one of the better performers, outperforming the titanium alloys. However, it does not meet the maximal thickness requirement, requiring a 0.55 meter thick blade thickness. Thus, we eliminate it. Next, we kind of move on to bending failure. Again, using the same geometric constraints and the wind pressure constraints. But instead of deflection, we evaluate that the blade cannot yield under the bending condition, once again, minimizing mass and leaving the free variables the same. We note from beam theory again, an expression for stress in terms of the bending moment. And we note that the maximum stress would occur at the base of the beam, at the top or the bottom of the beam, where it is furthest away from the neutral axis. Using this, we can evaluate an expression for the stress at yield must be greater than 1.125 times 10 to the 6 pascals. Also using this expression, then solving for B, plugging into our objective function, we can get an expression for the mass and a material index for maximization of the stress at yield to the 1/2 over rho. Evaluating this over our materials, we once again see CFRP and the wrought magnesium alloys are the best performers, and evaluate the thickness of the blade, the material index, and the mass under this condition alone. Again, plotting, we again can see how these materials perform with respect to each other, again, with CFRP being the furthest away from the line, and our line now having slope of 2 with sigma yield being to the 1/2 power.
Fourth design criteria is the centrifugal load limit. The function is still the same and the constraints are still the same for the most part, where now we're taking into account the centripetal force that will result in a stress in the beam. We still want to minimize the mass, and the free variables are still the same. So what we did is we took the centripetal force calculation and the equation, integrated it so that way we could find an expression for it and find using that to create the stress that is found in the expression below. We found that the tip of the beam is 7 times that of the wind speed, using that for our table that will be shown in the next slide. And we can see that all of the materials pass this criteria, as the differences for all of the materials are positive, and the greatest differences are the titanium alloys and the CFRP and their differences. And we do not have any further trimming of our selections.
Okay, so in order to whittle down our material choice to select a few materials, we decided to look at all the translations together, and all the materials that we look at have to pass all our translations and all of the minimum requirements in order to be viable for this. And the one we decided to consider to be the most important was the first translation, that being in total deflection at the tip. And we decided to do that one as it gave us the thickest beams total, while keeping both the length and the width constant. So another thing we had to consider was cyclic stress. So the fact that you have stress concentrations as these blades move around the central hub and while they're in operation, both whenever the beam is vertical due to higher wind speeds at the top, and also when it's in the vertical down position due to having to basically work against gravity, and that adding extra stress and more stress concentrations along the sides. So in order for that to be minimized, we decided to have a high factor of safety for both bending stress and also for centrifugal force, which we saw in the last few slides, and all the materials that we're looking at so far both have high factor of safeties there, so that's not as much of a problem. Same thing being with fracture toughness that we discussed in part 1, and all the materials there are also good for fracture toughness. And lastly, we also decided to look at surface temperatures, and we thought that the absolute maximum and absolute minimum temperatures in several states that would likely use these turbines, and we decided that a surface temperature range of between -60 and +60 Celsius was was the best here, and it covers the ranges for all the states we looked at. And when looking at the service temperatures for all of the materials that we had listed earlier, the only one that gets really too close is the magnesium alloys, and even then, it's only at the very minimum, at a very bottom that it gets close there, and that most likely is not going to happen very often in these conditions.
So now let's move on to the cost. After looking all the design criteria 2 was the one which derives the higher requirement of thickness of the blade. So using that, we'll be calculating the fabrication cost. We choose one best composite material and the best metal alternative. And as we saw, CFRP and wrought magnesium alloy were the top 2 candidates all across. We'll be using those to calculate total cost to manufacture. The fabrication cost is considered is assumed to be directly proportional to the surface area, both interior and exterior, which in cases of composites will include interior surface areas as well. Now, if we look at the table, we see the fabrication cost for CFRP, lower and upper bound both, significantly higher than $6 per blade of wrought magnesium alloy. When considered material cost into it and calculating the total cost, we find out that if we take $100 million of funding that we have been provided, we can only produce about 80 to 120 CFRP blades, but about 1,000 to 1,800 blades when using wrought magnesium alloy. So where CFRP has a lot of design advantage, wrought magnesium alloy gives a huge economic advantage. So let's see how we can make them. So CFRP manufacturing methods, there are 3 major commercially used methods: wet layup, pre-bed lamination, and resin transfer molding. Wet layup is an easy, least expensive and high skill requirement. Pre-bed is used for high precision applications, but when considering our application, we would recommend resin transfer molding, which is best suited for high volume manufacturing, where the dry fiber is inserted into 2 mold parts and the resin is inserted just while shutting out the clamp. So this way it is quick and be easy to produce high volumes. When we consider wrought magnesium alloy, they come in different forms of extrusions, as well as you can use sheet and plates and forge them into the shape and form that is required. Since magnesium alloys are ductile and there are a lot of variants which allow for hot extrusion in different forms, we recommend extrusion. And AZ31 is one of the best alloy which offers best combination of mechanical properties and extrudability. And there are many more where you can add on zirconium or other elements for work hardening or solution hardening or anything as per the application. And also they are easily weldable, so makes our fabrication an easy process. If we look at, in summary, all the design criteria, we find out that CFRP and wrought magnesium alloy has always been top 2 candidates, with CFRP outperforming significantly when considering design performance. But when we see manufacturing costs, wrought magnesium alloy provides a cheap way of manufacturing a decent wind turbine blade. So in summary, what we suggest is a mixture of wrought magnesium alloy blades and CFRP blades. What that means is, since we don't understand the proportions of power to mass ratio, and the power requirement is not well defined, the total number of wind turbines can have some having wrought magnesium alloys and some having CFRP blades. That way we combine best design performance and economic solution, giving us maximum efficiency and best economics.